Hi everyone, we are Alan, Iki, and Xinhan, and we are excited to introduce our team's project, an RFID-based smart tool cabinet. In our lab environment, tool borrowing and returning or other routine operations are common but error-prone process. To address this issue, we want to design an RFID-based smart tool cabinet that enables automatic tracking of borrowed and returned tools, significantly improving measurement efficiency and accuracy. The core research of the Inter project revolves around the materials. Firstly, electromagnetic shielding materials, and secondly, cabinet shear materials.
One of the important components of our cabinet would be this electromagnetic shielding. It has two main functions. First of all, it needs to suppress signal propagation from outside of the cabinet, and also it needs to form a stable electric distribution for the RFID scanning to work properly within the cabinet. And we have two constraints. The first one is the gap constraint. Since we're using the ultra-high frequency RFID signal, it needs to handle gap size less than 1 centimeter. And also it needs to handle the opening of the drawers. We have these objectives. First of all, we want to maximize the shielding effectiveness, and we hope to maximize the cabinet RFID reading rate. Finally, we hope to minimize the weight and the overall thickness of our cabinet. These are the three variables we get to choose from and do experiments on. That includes metal material selection, plate thickness, and the internal absorbing material.
Another key component of the smart cabinet is its enclosure. It provides structural support and serves as the base for attaching shielding materials. The enclosure protects tools from contamination and damage while ensuring secure storage. As part of laboratory furniture, it also reflects a high-tech image. When selecting enclosure materials, several constraints must be considered. These include manufacturing process limitations, cost, and cleanability requirements. Additionally, the compatibility between the substrate material and surface finishing methods must be taken into account. Our objectives are to maximize corrosion resistance, scratch resistance, and sheet strength for improved durability, while minimizing both cost and weight to suit laboratory use. The three variables in our design include the choice of material, surface finishing method, PVC film lamination, and coating thickness. Once the first prototype is completed, we'll conduct experiments to evaluate material performance. RFID tags will be placed both inside and outside the cabinet. The experiments aim to improve reading coverage inside the cabinet, reduce misreading outside, and identify the optimal combination of materials and thickness. The absorbing material's effectiveness will also be assessed. Evaluation will be based on tag detection rate inside and outside the cabinet, signal strength, and the distribution of signal dead zones. So that concludes our presentation. Thanks for your time.